Hello everyone, how's it going? We're going to be looking at the area under the curve in section 4.1, and so we're trying to estimate the area under the curve. And the reason that they wanted to estimate the area under the curve is the area under a velocity curve will give you displacement. And I mean, it's easy to find how far you've gone if your velocity is constant, but what if your velocity is not constant? And so, and there's lots of things like rockets taking off and dropping something to the ground that don't have constant velocity. Anyway, and the area under an acceleration curve gives you velocity. And if you're wanting other uses for finding the area under the curve, you could go to the preview of calculus on page 1 in your book and read about them, and it's kind of interesting. Anyway, so one way to, and there's other ways, but one way to estimate the area under the curve is to draw rectangles under the curve, because you can find the area of a rectangle. And then you can kind of see that if I use these 4 rectangles to estimate the area that's trapped between the curve and the x-axis. So that's when people say under the curve, they usually mean trapped by the x-axis. So it ends here at the x-axis. And so that area, you can see, just leaves out a little bit. And you can see that here that if I use these 4 rectangles, that it's a little bit, the rectangles are a little bigger than the area under the curve. And here, and it depends on how your curve is, and you know, if my curve changed and whatnot. And so it's not that the left would always underestimate and the right would always overestimate, but it happened here that it did. And so this is using the left endpoint for the height of the rectangle. So for this rectangle, it has 2 sides, right? The left and the right endpoint. So it's using the left endpoint for the height of that rectangle, whereas this is using the right endpoint. So this rectangle has this side, and it's using the right. And this rectangle has this side, and it's using the right for the height, and etc. And then here, this one, and for this particular curve, the midpoint happens to be very lovely, and the midpoint is using the middle of the rectangle for the height of the curve. And you notice that the midpoint happens to be pretty close to the area under the curve, because it's a little bit of an overestimate here and a little bit of an underestimate there, and so it's pretty close. So anyway, so we're going to be looking at finding the area under the curve, and some people call that a Riemann sum, and so we're going to give a try here and see how we do. And so I got things stacked up in the way. My office has become crazy today, and so my son would say that my office is his bedroom, and he is right, since he's moved home to help us while he's having to work from home, and so it's really a blessing. Okay, so here they're saying estimate the area under the sine graph, and you could totally graph the sine graph on your own from 0 to pi over 2. And so here I've just had Desmos graph it for us just to save us a little bit of time. And they want us to use right endpoints and to sketch the graph and the rectangles. And so the first thing that you would want to know is, well, if I was going to have equal size rectangles, how wide would each one be? Now, they don't have to be the same size, but it does make it easier to do this if they are. And so here is our A, and here is our B. And so this is pi over 2 minus 0 divided by N represents the number of rectangles, and it said 4 rectangles, so that's our N, so 4. And what delta X is the width. How wide is my rectangle, right? And so, and of course, the less wide your rectangle is, the better estimate you're going to have. And so if we do this, we're going to have, and you can use your calculator or your head, you're going to get pi over 8. Where did my equal sign go? Pi over 8. So each of our rectangles is pi over 8 wide. So we're going to have a rectangle that has a base that goes from 0 to pi over 8. And what I would like to use is, it said to use the right endpoint as the height of that rectangle. So between 0 and pi over 8, so that's how wide my rectangle is going to be, my height will be determined by the right endpoint. So that would be here at pi over 8. So this is going to be my rectangle right here. And then I have another rectangle, and that rectangle goes from pi over 8, and you would add pi over 8. Pi over 8 plus pi over 8 is pi over 4. And that's how wide that rectangle is going to be. They're all going to be the same width. And we're going to use, not pi over 8, because they said to use on the right. So we're going to use the right endpoint as the height. You hear that rain coming down. Bring the rain, I say. And then we're going to do it again. We're going to have 4 rectangles. So far I have 2. So the next rectangle is here. Here's the base of it. And I'm going to use the right endpoint as the height. And one more time. And I'm going to use here the right endpoint as the height. I could have got crazy and got my ruler out. Okay, and so we're going to be finding the area of those 4 rectangles, and we're going to use it to estimate the area under the curve from 0 to pi over 2. And so we didn't need to go further, right? They didn't say to go further than pi over 2. My graph went further, just, I don't even know why my graph went further, but my graph did go further. Anyway, maybe to be nice and the right size or whatever, I don't know. Okay, so how I come up with the area of this rectangle and how you find the area of any rectangle is you multiply how wide it is by how tall it is. And how tall that rectangle is, we used x equals pi over 8 to determine how high it was. And remember, this curve was the sine curve. So how tall this rectangle is right here is actually sine of pi over 8. And how tall this rectangle is actually sine of pi over 4. And how tall that rectangle is actually sine of 3 pi over 8. And how tall this rectangle is actually sine of pi over 2. And I know that sine of pi over 2 is 1, and I can see, oh yeah, that's right there at height 1, right? And so going across. And so now what I would do for each of my rectangles to find the area, this is approximately the area under the curve, is I would multiply pi over 8, how wide it is, times how tall it is, sine of pi over 8. And then plus, and then I would multiply how wide it is times how tall it is, sine of pi over 4. And again, and if you had different widths, then you would have pi over 8 on all of them because they're all the same width. And so this is sine of, what is that, 3 pi over 8? And plus pi over 8 times sine of pi over 2. So this is approximately the area under that curve. And I'm just going to get my calculator out and put that in. Now one thing, because they all have pi over 8 in common, you could just factor out a pi over 8, and that makes it a little bit easier to put in your calculator. So I'm just going to, when I put this in my calculator, I'm going to do pi over 8 and then parentheses, and make sure your calculator is in radians. If you get your calculator in degrees for calculus, I think most of the time we're in radians. And so my calculator used to be borrowed all the time by one of my kids who was taking physics, and they would give me back my calculator and it would be in degrees. And then I would do something and think, you know, gosh, the last time I did that I got a different answer, and be thinking what happened, and thinking I'm going crazy and all of that, and then realize, oh, my calculator is in degrees. So anytime something is not coming, you're doing trig, and it's not coming out the way you think it should, that's a good thing to check, is that did you have your calculator in degrees? So I'm getting here 1.1834, and I didn't remember if they told me how many places to take that. And so if I wanted to take it 3 places, there would be 3 places. If they asked me to take it 4 places, I could take it 4 places. So they didn't say. They asked me to sketch the graph, which I had sketched the sine graph for you, and then they asked us to sketch the rectangles and the sine. So I sketched the sine graph for you, and then we sketched the rectangles in there. Now they're asking us, hey, is that is your estimate? So this is our estimate. Do you think it's an overestimate or an underestimate of the area under the curve? And so yeah, it's an overestimate, right? And so now they're going to ask us to try that again. And so so this is part B, and they're asking us to use the left endpoint. And so the same deal as far as 4 rectangles, and still going from 0 to pi over 2. And so here's the base of our rectangle right there, and the height is at 0. So actually there's no rectangle here, right? And so because you would use the left endpoint. And then for the next rectangle that goes from, so the next one, I don't know if I have a different color pen, but if I did have a different color pen, it would be going from right here, right? And they said to use the left endpoint. So the left endpoint is here. And I'm going to draw that across. So here's my rectangle that's estimating it, right? And so I'm going to find the area there. And then the next one, I should have used the pen on the other one. I might spend too much time just coloring, and you guys would be like, oh, that video was just of my crazy teacher coloring. And so there we have that one. And one more. And we're using between here and here, we're supposed to use the left. Okay. And so when we look, the height of this rectangle, which is not a rectangle at all, though, is sine of 0. And the height of this rectangle is sine of pi over 8. And the height of this rectangle is sine of pi over 4. And the height of this rectangle is sine of 3 pi over 8. And so my area, using the left endpoint. Now I think that in the book they get kind of fancy with the name, and I think that they call this an L4 for left endpoint and 4 rectangles. And you could definitely call that, and you can probably guess, what did they call the one where we use the right endpoints? Yeah, R4. And then midpoint, what do you think? Yeah, M4. And so they really got technical on that. You could just call it the area. That's good. And so, so anyway, so that's approximately equal to pi over 8 times, and I'll just factor out the pi over 8 on this one, sine of 0 plus sine of pi over 8 plus sine of pi over 4 plus sine of 3 pi over 8. And you probably notice that, hey, they have some in common, right? And so instead of starting the one before, right, started at sine of pi over 8, that's actually our second term here. And instead of ending at sine of pi over 2, right, we have that term That's here. Instead of ending there, it's ending at sine of 3 pi over 8. So I could actually come here and delete this out just a little bit. I already kind of have that in my calculator. And what would I replace this last one? It was sine of pi over 2. Do you guys agree? Sine of 0, and which is 0. And so now this is my estimate here. The area is approximately equal to 0.79, and I can't remember, did we say we were taking it 3 places? Is that what we decided to do? Yeah, that's what we decided to do. And they didn't tell us how many places to take it, and I would have followed their directions. And do you guys agree that that's an underestimate, right? Then they're asking us to use the midpoint. And so we're going to do that as the height. And so the midpoint, this is kind of nice. I have the boxes all set up, right? And so here's the midpoint, and they're wanting us to use that as the height. And so now we have to figure out, well, where is that midpoint right there? And you could do pi over 8 minus 0 divided by 2. That would find it. Oh, and then I would get that out of my calculator. So is that, I'll show you, pi over 8 minus 0 divided by 2. Is that pi over 16? And then the next one here in the center, you could do the same trick. You could do pi over 4 minus pi over 8, right? Or you could, and that divide by 2 to get in the, would that give me the center there? My dad is calling. I will call him back. Had some emergencies in our family today. That's there. That gives me that one. I think I just need to add pi over 8 to get to the next one. Oh my gosh, I'm not thinking, and I'm so tired. So this is, oh yeah, I could just count that out, right? Be smart, my friend. I'm talking to myself here. 1 pi over 16, 2 pi over 16, 3 pi over 16, 4 pi over 16, 5 pi over 16, 6 pi over 16, 7 pi over 16, 8 pi over 16, right? And I'm going to use the middle here on all of them. Boy, that rain is coming down. I love rain. It's all I can do not to run out there and get in it and just let it come down on my head. Okay, now we're going to find the area under those 4. And that area, also called M4, is approximately equal to pi over 8, that's how wide the rectangle still is, and then times the height of each rectangle, right? And I'm factoring out a pi over 8. So that would be sine of this one's height is sine of pi over 16, sine of pi over 16, plus sine of 3 pi over 16, plus sine of 5 pi over 16, plus sine of 7 pi over 16. And you could definitely see that why it would be better to have a computer do it for you than yourself, but they're just trying to give us the idea of how we would find it, right? That's all that's happening here, is getting the idea, not that people would want to do this by hand. although people did do this by hand. But the idea of how I could find the area, how I could estimate the area under the curve. And they give you plenty of reasons, including finding displacement and velocity for wanting to do that. Now I've been talking instead of paying attention to my calculating, so I know that some of you are going to send me an email and tell me that I goofed this calculation up. And I'm going to be so tired today that I'm going to not care, but then tomorrow I'm going to have to fix it because that's how I am. So I wish I would have looked up the answer and made sure, since I was talking at the same time as I was typing. And so this I get somewhere in this. At least it's in between those two. And you have to admit that it asks you, is it an underestimate and overestimate? And it's pretty hard to tell, right? It could go either way on that because this is about that same size. So this was over, but that was under, and they're about the same size, so maybe a wash. And same here. And of course my drawing of them isn't perfect. And so I'm not sure. It's pretty good is what I'm going to say. So it's a pretty good estimate. The midpoint isn't always the best estimate. That's not the point here. That for this particular drawing, it was good. But anyway. Okay, so here's when you have constant velocity, it's easy because people always tell me, are you sure that underneath a velocity, the area under a velocity curve is going to give you the displacement? And if you have constant velocity, it's really obvious that, yeah, it is. So here's the velocity of 30 miles an hour, right? So here it is. My velocity equals 30 miles per hour. And if I go for 2 hours, so here's 2 hours, here's 0, from 0 to 2 hours, then how far did I go? Well, it's just the area under that curve, right? And so as the velocity is constant, then it's really easy. So I went 60 miles. And of course, if you just have constant velocity, well, the distance is just the rate, which is 30 miles per hour, times the 2 hours, right? And that's 60. And so the miles. And so if you have constant velocity, there's no reason to find the area under the curve. But what if your velocity is not constant? And there's lots of things that have non-constant velocity. And so that was why Newton was so interested in this, because remember that he had an apple fall and hit him on the head. And people say that's when Newton invented gravity. Discovered gravity, or whatever you want, whatever words you want to put in Newton's mouth right there. But the real story, at least in my story, in my opinion, is that people knew when you drop something, they knew that it would go to the ground. And it was Newton who started talking about when you drop something, does it go the same speed all the way to the ground? Or does it speed up? Or how does it go? And what governs all of that? And with gravity. Okay, so this is one other problem. And I mess this problem up every single time. And so without some of you to get me back on track, I know I'm going to mess this up. So people are saying, don't be so negative. You can do it. But why I mess it up is this is time in seconds, and that's miles per hour. And so, and that's my problem right there. So now that I've gotten it out in the open, what my problem is, we'll hopefully be able to not have that problem. So the table shows the speedometer reading at 10-second intervals during a 1-minute period for a car racing at Daytona International Speedway in Florida. Estimate the distance the race car traveled during the time period using the velocities at the beginning of the time intervals. And so we'll go ahead and do that. So we have a mismatch. And so you have choices, and your choices are to either convert our time in seconds into hours, or convert hours into seconds. And then since we're trying to figure out how far the car went using the velocity at the beginning of each time interval, and you could draw it out if you wanted and just kind of see kind of how that went on that, on just to get the heights and all that. So you could definitely do that. But you can't have this mismatch of the time unit. Let me just draw it just so that you can see just a little bit. So here at time 0, the car is going 182.9, that's precisely there. And then at time 10 seconds, the car is going precisely right here, 168.0. And so if I wanted to get a rectangle there to estimate the area under that curve, which would then be the velocity, they told me to use the beginning, and so my rectangle would be here. And then the next one goes between 10 seconds and 20 seconds, and they told me to use, for 20 seconds was 106 miles an hour, 106.6, and they told me to use the beginning of the time interval, which was right here at 168. So, oh, here was my 168, sorry, right here at 168. And then the next one was between 106 and 99, and they told me, so here's 99 right there. Doesn't matter my scale, right? I'm not even trying to make my scale good, just drawing it up so that I have, so this height was at 182.9. This height was at 168.0. This height was at, and my got all messy, you know, have you ever got messy in your drawing? When you're drawing in pen, if you're going in pen, you're going to get messy and you're not going to be happy. Everyone's going to frown. Oh my goodness, I have had too much tiredness today, haven't I? Okay, so this was a height of 182. This one is a height of 168. This one is at a height of 106.6. This one's going to be at a height between 30 and 40 of 99.8. And then between, so that's 40. And then between 40 and 50, it's going to be at a height of 124. And I don't even care the scale, it doesn't matter that much. 124.5. And then between 50 and 60, it's going to be between 50 and 60, it's going to be at 176.1. And so then to find the area, do you guys agree that's 10 seconds, right, is in the, for each one of them. And let's see, 10 seconds times 60 seconds, 1 minute, and 60 minutes, 1 hour. And so I've decided to convert that because I want my distance in miles, and so I've decided to convert that into hours so that I can use these times here. So you get to choose whatever you want. Whatever you want to convert, you can convert all them if you want. And so I get 1 over 360 of an hour. Okay, so 10 seconds is 1 over 360 60ths of an hour. So my area, which is my velocity, right, is approximately equal to 1 over 360, that's how wide it is, times 182.9, and then plus 100 over 1 over 360 times 168.0, all the way down to 1 over 360 times 176.1. Notice this one didn't get used because of the beginning of the time interval, right? We used all the others. And so our, this wasn't our velocity, this was our displacement, right? Our area equals our displacement. Oh man, I'm not doing too good. Okay, so we're gonna find that. And so I'm gonna factor out a 1 over 360 to the front. And I'm gonna multiply this 182.9 plus 168.0. Man, the rain is coming down. I love it. And it's a good time too, because that makes all those flowers bloom. Oh, I love that. So our displacement is 2.38, and this was miles, right? And you could look at the units. The time here was 1 over 360 hours, and this was miles per hour. So I have hours times, and then all of those are miles per hour times mile plus miles per hour, right? Dot, dot, dot. So when you add them all together, they're miles per hour, and hours times miles per hour is just miles. So that's our estimate. It didn't say where to round to, so I'm going to call it good. And I want to hit before the 35-minute mark because it cuts into a second video. Using rectangles to approximate the area in their curve is called a Riemann sum. And what really helps is to have more rectangles. So having just 1, 2, 3, 4 rectangles didn't do that good of a job. Having more rectangles did a little better job. Having even more rectangles did a better job. And having even more rectangles even did a better job. This is an interactive thing in Cengage, and you can make it do this and have however many rectangles you want. They like to have some fancy notation in the book as well. And in some semesters we have a lot of time and we go over all that fancy notation. In other semesters we have the coronavirus and we don't do as much on it. But you can look at all the fancy notation that you want, and Andrea absolutely loves it. So this is the sum sign, which means add them all up. And what you're going to be adding up is the height of each rectangle. And I'm going to count my rectangles off. Rectangle 1, rectangle 2, rectangle 3, rectangle 4. That's all that's going to do, times how wide each rectangle is. And you notice that's what we did here, right? How wide the rectangle was times how high the rectangle was. How wide times how high. I think it's helling out there. That's what it sounds like. A good approximation happens when n goes to infinity. So the number of rectangles goes to infinity. And when the number of rectangles goes to infinity, think about the formula. B minus A divided by n is what delta x is. And so if this is going to infinity, what's delta x going to? It's getting close to 0. So the width of your rectangle is getting close to 0. Okay, my lovely friends, that's all we're going to do today because I'm pretty wiped out, but on Monday we'll do more.